this episode, we're going to build a beginner-friendly foundation for control logic, which is the set of instructions that tells controllers how to behave when they read inputs and drive outputs. If you have never worked around industrial automation, control logic can sound like software engineering, but it is best understood as a disciplined way to express how a process should respond to conditions in the real world. Control logic is what turns sensor signals into decisions and actuator commands. And because those decisions can move machinery, open valves, start motors, and trigger shutdowns, the logic has real consequences. You do not need to learn how to program controllers step by step, but you do need to recognize the common logic styles and understand what each one is good at. The exam is likely to ask you to identify what a given representation is, what kind of problem it fits, and why changes must be controlled carefully. Once you understand the big four styles in this title, you will be able to read descriptions of OT systems with far less confusion. You will also start to see why security in OT often focuses on preventing unauthorized logic changes and ensuring that logic behaves predictably. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Author.me in the Bare Metal Study Guide series. A helpful way to begin is to separate control logic from general-purpose software in your mind. General software might handle many kinds of tasks, like web browsing, file storage, and complex user interfaces, and it can tolerate variable timing and occasional delays. Control logic, on the other hand, is often designed to execute in predictable cycles, repeatedly scanning inputs, evaluating logic, and updating outputs. This scan cycle creates a steady rhythm that makes the physical process predictable, which is important for stable control and safety. The logic is usually designed around the idea that the controller is always awake, always watching inputs, and always ready to react. That does not mean the logic is simple, but it does mean it has a strong focus on determinism and reliable outcomes. Another key difference is that control logic is often built around discrete signals, continuous measurements, and state changes, rather than around user-driven actions like clicking buttons. A beginner should also understand that control logic is often tied to a physical system's design. So changing logic is not like updating an app. It is more like changing the rules of how a machine behaves. That is why logic changes are treated as operational events with safety and availability implications. Ladder logic is one of the most recognizable forms of industrial control programming, and it was designed to feel familiar to people who worked with electrical relay circuits. The ladder idea comes from a diagram-like representation with two vertical rails and horizontal rungs, where each rung represents a logical condition that can energize an output. In plain terms, ladder logic is a visual way to express if this set of conditions is true, then turn on this output, or if a certain safety interlock is active, then prevent an action. The conditions often represent inputs like switches, sensor states, or internal flags, and the outputs represent things like motor starters, solenoids, alarms, or internal memory bits. A beginner should think of ladder logic as a practical, readable way to describe on and off decisions, interlocks, and sequences that look like electrical control behavior. One reason ladder logic persists is that it can be easy for technicians to interpret, especially for discrete control tasks like conveyor systems or machine start-stop logic. From a security standpoint, the readability that helps maintainers also means that unauthorized changes can be hidden in plain sight if people are not watching for them, which is why change control and access control matter. Understanding ladder logic helps you recognize why OT teams care about who can modify logic and how those modifications are reviewed. Function block diagram, often written as FBD, is another common way to represent control logic, and it is especially useful for showing how signals flow through a set of functional components. In FBD, you can imagine logic as a series of blocks, each performing a function, such as adding values, comparing measurements, applying filters, or implementing control actions, and the blocks are connected by lines that represent signals. The key beginner idea is that FBD is about relationships and data flow, making it well suited for continuous processes where analog values matter, like temperature, flow, and pressure. If ladder logic feels like wiring relay logic for discrete events, FBD feels like connecting processing elements in a pipeline where the output of one function becomes the input to the next. This makes FBD intuitive for control loops, calculations, and signal conditioning, where you need to transform sensor readings into a control output. Because FBD resembles a diagram, it can also help people communicate how logic behaves, which supports troubleshooting and review. Security-wise, FBD can be changed in ways that subtly alter behavior, such as modifying a scaling factor, a limit, or a comparison threshold, and those subtle changes can be hard to detect without good review practices. Beginners should learn that control logic is not only about big, obvious actions like turning a motor on, but also about small numeric decisions that affect stability and safety. Recognizing FBD helps you understand where those numeric decisions might live. Structured text is a more code-like language that looks closer to traditional programming, and it is often used when logic requires more complex expressions, loops, or operations that are awkward to express visually. In structured text, logic is written as statements that can include conditions, calculations, and variable assignments, making it powerful for more advanced control tasks. A beginner does not need to learn syntax, but should understand why this style exists. Sometimes a visual diagram becomes too large or too messy, and a text-based approach becomes clearer and easier to manage. Structured text can be good for algorithms, complex decision trees, and manipulation of data structures, and it can support reuse of logic patterns across similar equipment. The trade-off is that it may be less approachable for people who are used to wiring diagrams and visual representations, which can influence who can review and troubleshoot it comfortably. From a security perspective, text-based logic can hide changes in small details, like a single operator or a subtle condition, and those changes can significantly alter behavior. This is why version control, peer review, and controlled access are important, even if the environment does not use those practices in the same way as Office software development. Beginners should remember that control logic is still logic, and logic can be changed intentionally or accidentally. So the ability to recognize the representation helps you understand what kind of oversight is needed. Sequential Function Chart, often written as SFC, is designed to represent processes that move through stages, steps, or modes in an organized sequence. Many industrial processes are not just continuous loops. They involve sequences like startup, normal operation, shutdown, cleaning, batching, or emergency handling. SFC helps express these sequences by defining steps, transitions, and actions, where the system is in one step until a condition is met, then it transitions to the next step. The beginner-friendly way to think about SFC is as a flowchart-like view of process states, where each state has rules about what happens and the transitions define when the system changes state. This representation can be easier for humans to understand when the process has clear phases, because it mirrors how operators often think about the operation. SFC can also help avoid tangled logic by separating what happens in each phase rather than mixing all conditions together. From a security perspective, SFC is sensitive because changing a transition condition or skipping a step can alter the sequence in a way that creates unsafe or unstable behavior. An attacker or a mistake could change when a shutdown triggers, how long a step lasts, or whether interlocks are respected during transitions. Recognizing SFC helps you see that safety can depend not only on the control values, but also on the order and timing of actions. Even though these four styles are different, they are often used together in real systems, because each one fits certain kinds of problems well. A single controller program might use ladder logic for discrete interlocks, FBD for analog control calculations, structured text for complex computations, and SFC for high-level sequencing. This mix can confuse beginners, but the right mindset is that the controller is not choosing one style as an identity. It is choosing the best tool for each part of the job. That means when you see a question about identifying a logic type, it may be describing a piece of the overall system rather than the whole system. It also means security controls must protect the whole program, because a small change in one part can affect behavior elsewhere. Another important beginner concept is that these logic types are different representations of the same core idea. Transform inputs into outputs according to rules. The representation changes how humans understand and maintain the logic, and that human factor matters in both safety and security. If a representation is harder to review, it can be easier for errors to slip through. If a representation is very readable, it can still be risky if access is too broad. Understanding the differences helps you reason about both operational and security implications. A common misconception is that control logic is always about simple on and off behavior, but modern control often involves continuous values, timing, and complex interactions. Another misconception is that logic is fixed once installed, but in real environments, logic changes over time to improve performance, adapt to new equipment, and respond to incidents. Those changes are necessary, but they also introduce risk, which is why change management is such a big theme in OT. Beginners sometimes assume that because a controller program is just software, it can be updated the same way as Office software. But the cost of a logic error can be much higher when it affects physical processes. There is also a misconception that visual logic is always safer because it is easier to understand. Yet visual representations can become complex and crowded, and that complexity can hide mistakes. Likewise, text-based logic can be clear and structured when written well, but subtle changes can be hard to spot without disciplined review. The takeaway is that no representation is inherently safe. Safety comes from correct design, careful review, controlled access, and testing. The exam often tests whether you understand that the process context and the change process are as important as the logic style itself. From a security viewpoint, it helps to think about what it would mean if the logic was wrong or altered. If ladder logic interlocks are changed, a machine might run when it should be blocked, or a safety condition might be ignored. If an FBD calculation is changed, a control loop might become unstable, leading to oscillations or overshoot that stress equipment. If structured text conditions are altered, the system might behave differently in edge cases, like during abnormal readings or failures. If SFC sequencing is modified, the system might skip checks or move to unsafe steps too quickly. In all cases, the result can be degraded reliability, quality problems, safety incidents, or costly shutdowns. Security controls aim to reduce the chance of unauthorized changes, but also to make authorized changes accountable and reviewable. That includes knowing who can edit logic, how changes are approved, and how the system can be restored if something goes wrong. Even without discussing specific tools, you can understand the principle. Logic is a high-impact asset, and protecting it is central to OT security. When exam questions ask about protecting critical components, logic integrity should be near the top of your mind. To close, control logic is the foundation that turns OT from a collection of devices into a functioning system, and the 4 representations in this lesson help humans build and understand that logic. Ladder logic expresses discrete control and interlocks in a relay-like visual format. FBD expresses signal flow and functional processing that fits analog control. Structured text expresses complex logic in a code-like form, and SFC expresses stage sequences and transitions for processes with phases. Real environments often combine these styles, choosing each where it fits best, which is why you should focus on function rather than assuming a system uses only one. The key beginner skill is recognizing what each representation is meant to communicate and why changes to any of them must be controlled carefully. If you can explain these logic types in plain language and connect them to process behavior and risk, you will be able to reason through many security OT+ scenarios without getting lost in terminology. That clarity will carry forward into later topics, because understanding logic is the first step to understanding how control loops behave, how monitoring works, and why OT security must protect both data and decisions.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.